Let's talk about degrees of unsaturation in organic compounds by comparing structures of alkanes, alkenes, and cyclic compounds. Let's begin with pentane. Pentane is a saturated compound that can be fit into the generic alkane formula of CnH2n plus 2. Therefore, since we have 5 carbon atoms, C5, we have 2 times 5 plus 2, 12 hydrogen atoms. Now what happens if we compare it to pentene? Go ahead and construct a double bond between carbons 1 and 2. To do so, I need to sacrifice one hydrogen atom from the respective carbons. So in order to form a double bond between carbons 1 and 2, I have to remove one of the hydrogens from here and one from there. So minus 2 hydrogen atoms, I will have pentene, which compared to the saturated alkane analog has 2 fewer hydrogen atoms. The formula of pentene is CnH2n, or in our case, C5H10. For each double bond that we construct, we have to remove 2 hydrogen atoms from the alkane analog or precursor. What happens if I want to make a cyclic compound? If I want to close the ring between carbons 1 and 5, I have to again remove one pair of hydrogen atoms, one from carbon number 1 and one from carbon number 5. This will give me cyclopentane, which again is 2 hydrogen atoms shorter in chemical formula than the corresponding pentane analog. The formula of the cyclopentane is C5H10 because we removed 2 hydrogen atoms. We say that each ring and each pi bond is equivalent to 1 degree of unsaturation, 1 du in cyclopentane, and 1 degree of unsaturation, 1 du in the pentene compound. What happens if we construct 2 pi bonds? I would have to remove additional pair of hydrogen atoms to form the triple bond between carbons 1 and 2. Triple bond, I have a sigma bond and 2 pi bonds. Those are carbons 1 and 2, 3, 4, and 5. I have 2 degrees of unsaturation because I removed 4 hydrogen atoms, or 2 pairs of hydrogens. My formula is now C5H8. 3 hydrogens over here, plus 2, 5, plus 2, 7, and acetylenic hydrogen at the end. So again, each time we construct a pi bond or a ring, we introduce 1 degree of unsaturation. Let's go ahead and try to predict the number of degrees of unsaturation given some chemical formulas, and then let's go ahead and draw a plausible structure for each, which is part of structure determination. How do we do it? We want to take our formula and reduce it so that it doesn't contain any heteroatoms. The rules for replacing nitrogen and halogen with atoms with hydrogens, as you recall from the lecture, is to subtract the number of hydrogen atoms for each nitrogen and to add 1 hydrogen atom for each halogen present. As for oxygen and sulfur, since these will form two single bonds or one double bond to carbon, they serve as bridges and we can simply ignore them in structure determination when we're trying to calculate the number of degrees of unsaturation. Using those rules, therefore, I can reduce the formula to C8H. For nitrogen, I will subtract one hydrogen from the 6 present, which will give me H5. I ignore oxygen and sulfur, and for chlorine, I add one hydrogen atom. So from H5, I go back up to H6. Therefore, my equivalent without the heteroatoms has the formula of C8H6. H6. Next, I want to compare this formula to the saturated analog of a C8 compound. In other words, I want to inscribe this formula into CnH2n plus 2. Since I have 8 carbon atoms, then for a saturated compound, I would have to have 2 times 8 plus 2, 18 hydrogen atoms, because aliphatic compounds have general formula of CnH2n plus 2. Therefore, for 8 carbon atoms, I need to have 2 times 8, 16 plus 2, 18 hydrogen atoms. Now I have two formulas without any heteroatoms, and I want to compare the number of hydrogen atoms present in each. I have 18 hydrogens in the saturated analog versus 6 hydrogen atoms in the compound in question. Since for each DU I am short of 2 hydrogen atoms, I divide the difference by 2. So 18 minus 6 is 12 divided by 2. I have 6 degrees of unsaturation. 6 degrees of unsaturations would give me any combination of rings, double or triple bonds. Let's go ahead and draw one plausible structure. I have 8 carbon atoms, and that's where we'll start. Let's go ahead and draw some formula that has 6 plus 2, 8 carbon atoms. I'll start with cyclohexane, and I will add 2 more carbon atoms. So now I have 8 carbons, and I already have 1 degree of unsaturation because I have a ring. I need 5 more degrees of unsaturation. I will draw 3 pi bonds, effectively drawing a benzene ring that has 4 degrees of unsaturation. 1, 2, 3 for the pi bonds and 1 for the ring. That's 4 degrees of unsaturation. I need 2 more. I will construct a double bond. So now we have styrene, that's 5 degrees of unsaturation, and I need 1 more. Looking at the formula, I see that I have NO2 or nitro unit. Nitro substituent has 1 DU built in because when you draw it out, you see that nitrogen will have oxygen connected by double bond and another oxygen connected by a single bond. So there is a formal negative charge on oxygen and a formal positive charge on nitrogen. 1 Du comes from the double bond between nitrogen and oxygen. Now I have 6 degrees of unsaturation. Let's verify it. 1 second for the ring, 3, 4, 5, and 6. Now I need to add heteroatoms. I already added nitrogen and 2 oxygens. Now I need to add sulfur and chlorine. I will put sulfur in the form of a thiol over here. Be sure to draw hydrogens bonded to all heteroatoms. And I need to add chlorine. I will put chlorine at the vinylic position over here. To verify, I have 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. I have 1, 2 for the ring, 3, 4, 5, 6 degrees of unsaturation. Next, I'll check that all of my heteroatoms are present. Nitrogen is over here. 2 oxygen atoms, sulfur, and chlorine. Given that I have the correct number of carbon atoms, heteroatoms, and degrees of unsaturation, it is not necessary for me to check for the correct number of hydrogens, which should be 6. Just to verify it, I will draw all of the hydrogen atoms. 1, 2, 3, 4, 5, and 6. Let us do one more example. Our next compound has 13 carbon atoms. So I will reduce it to C13. And as for the hydrogen atoms, I will subtract 1 for nitrogen, which will give me H13. I will ignore oxygen, and I will add 1 for the halogen, which will give me H14. I have C13H14 compound. I will compare it to the saturated or aliphatic compound, which should have C13, and when I inscribe it into Cn, H2n plus 2, where n equals the number of carbon atoms, 13 times 2 is 26, plus 2, I should have 28 hydrogen atoms. I have 28 hydrogen in a hypothetical saturated compound versus 14 in the compound in question. I will compare the number of hydrogen atoms. The difference is 28 minus 14 divided by 2, which gives me 7 degrees of unsaturation. Next, I will construct a structure that has 13 carbon atoms. I will begin by drawing 2 fused cyclohexane rings. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have 13 carbon atoms. I need 7 DUs. I have already 2 inscribed into the ring, so that's 2, 3, 4, 5, 6, 7. That's naphthalene, 2 fused benzene rings. So again, 2 for the rings, 3, 4, 5, 6, 7. We have all of the degrees of unsaturation present. Next, I will include nitrogen in the form of an amine group, for example, NH2. Again, be sure to include hydrogen atoms bonded to oxygen or nitrogen. I also need 1 oxygen atom, OH, for example, and a bromine atom. I will verify that I have 13 carbon atoms, 2, 6, 7, 8, 9, 10, 11, 12, 13. I have 2 degrees of unsaturation for the ring, plus 3, 4, 5, 6, 7 for the pi bonds, and I have nitrogen, bromine, and oxygen, which gives me a plausible chemical structure for the unknown compound.